afternoon, everyone. I'll start with the first one of the two sections. They're both chapter 9. The first one is chapter 9, and we're going to look at what's called the introduction to sampling distributions. So before we get too deep into that, let's do a quick summary of hopefully things that we know and add some terms that you haven't met yet. So we have a thing called the population. So the population would be everybody that you're interested in. So you might be interested in Scottish people, in which case the population would be all Scottish people. You might be interested in asking a question about high school students in America, in which case the population would be high school students in America. Right? And then we have a thing called a sample. Now, would you agree a sample is just a small group of people from the population? And you can collect samples in all sorts of ways. But we're just going to assume that for the purpose of simplicity, that all these samples are just simple random samples, right? We collect them, the best type of sample you could. Now, normally you have a population that you're interested in some value, some number. It might be, I'm interested in their average age. Right? So, oops, almost got that back to front. There we go. Can you remember that funny little Greek symbol? It's pronounced mu. It's the mean. So you might be interested in the mean of the population. You might be interested in a thing called that. Isn't that a Greek letter sigma? And what does sigma represent? What would that be? Starts with an S. What does sigma tell you about a population?
Standard deviation.
Right. And you might be equal to this, looking at this, and we'll use the letter P, and that's the population. Kind of get my R in there, proportion. Can you imagine you went and asked everybody in the high school, do you take drugs? Then P could be 0.2, right? Or 0.02, whatever it might be. So you've got a mean, a standard deviation, and a thing called the population proportion. Population proportion is a decimal, right? It's somewhere between 0 and 1, and it's the proportion of people who said yes to whatever the question was, right? Standard deviation and mean are a little bit different from that, aren't they? They're based on the calculation, you know, adding them all up, divided by how many, and the standard deviation is a measure of how spread out the data is. Now, when you do a sample, you typically calculate similar things. But isn't X bar the mean? Isn't that the symbol that we use to represent the mean of a sample? What symbol do we use? There's a couple of symbols, but what symbols do we use? I think I should put this outside, it's easier to read. What symbol do we use to represent the standard deviation of a sample? There's at least 3 I can think of. Don't we sometimes use S? Use that some, yeah. I've used SD. Have you ever seen, especially in calculators, S with a little baby X? They're all the same thing, right? But we just tend to use more choices there. The one that you probably haven't seen yet is if you asked 200 students, do you take drugs? The answer you get from a sample is called that guy, and you pronounce it, you say it out loud as p hat, and that is the sample proportion. So some of these terms you've seen before, these last two, less likely to have seen them before, right? These things belong in a population, that's numbers that you get from a population. These are the equivalent numbers that you would get from a sample. If your number comes from a population, it's called a parameter. So all of these things are called parameters. And if you get the numbers, these ones here, and you get them from a sample, these are called statistics. In fact, isn't that where the name statistics comes from? That's, if you're wondering where the term statistic came from, it comes from the names that we use for these things. So far, so good. This is just vocabulary. What does words mean? There's not a great deal that they're going to ask you in this section. I'm just doing a quick scan through before I show you them, make sure there's nothing that I should have mentioned that I missed. Oh, excuse me. No, okay, we are ready to look at the homework then. A lot of the questions in this homework are going to be really quick. It's those that give you a question and there's 4 or 5 dots to pick. A lot of them are going to look like that, okay? So maybe make this a little bit bigger, hopefully. Not too big, okay. Right, here we go. In each of,
You might want to turn off the key.
I may want to turn, the darn thing has a default that it does this. I should have paid attention. Close it off. We'll make your questions really easy, I guess, but let's pretend that we don't know what they are first. Right, okay, I think we're ready now. Okay, in each of these situations, the thing that's bold, so in this case, it's that guy there, is it a statistic or a parameter? So let's look at it. A polling organization samples 1,000 adults and finds that 71% of the sample wanted tougher drunk driving things. What would that be, a statistic, that 71, or would it be a parameter?
Statistic.
Yeah, I mean, the minute you see the word sample, isn't the answer almost done? Samples give you statistics, populations give you parameters. Now, of course, there are 2, I believe, is it? Yeah, 2 statistics. Is it a statistic because it's a population value, or is it a statistic because it's a sample value? I hope you'd all say that's a dumb question. It's obviously that one, and you're good to go, right? Are we comfortable that these questions are going to be pretty much the same as that one, right? I have no idea where I'm going, so I'm going to go to D now. A writer wants to know how many typing mistakes are in one book, one manuscript. So hires a proofreader who reads the entire, it's an important word here, manuscript, and he finds 16 errors. The entire manuscript. Right, is this 16 a statistic or a parameter?
Parameter.
Agreed. Didn't you read the entire book? So it's basically the population is the book, right? Is it a parameter because it's a population value, or is it a parameter because it's a sample value?
Pop value.
Right. Anytime it's a parameter, isn't it going to be the population value? And every time it's a statistic, it's going to be the statistic value. So once you've done 2 of them, you'll never make a mistake, right? You'll always go parameter is population, statistic comes from a sample. Okay, I may have to shrink this back a little bit. A polling organization plans to sample 1,000 adults. and they want to do it to estimate the proportion of Americans that think that crime is a serious problem in this country. In the context of this poll, explain the difference between a statistic and a parameter, and what is the parameter of interest to the polling organization. Okay. The parameter of interest is a proportion that think crime is a serious problem. Would you agree that's what they want to know? Right, so that's the parameter of interest, is what do you want to know from the population? Do you see, if I read a little bit further, can you see the word population at the end? So I know that the parameter of interest is the percentage of people who think it's a proper thing. Now, the statistic will be the proportion of that 1,000 who think that this is a serious crime, and its value will be known after the poll is taken. The statistic will estimate the unknown value of the parameter. Does that complete sentence make sense now? Isn't that pretty much the basis behind every sample? I'd like to know what the answer is for the population, but I can't afford to ask everybody. So I'll ask 1,000 people, and won't you use that answer that you get to estimate the population parameter value, right? So I want to know the age of every American. Too much money to ask all of you. So I'll find 1,000 of you and get your average age. Won't the sample's average age be at least an estimate of the population average age? My statistic, right, the sample of my, the mean of my sample, is an estimate of the population mean, which is the parameter. You can go through that one. Okay, this one, you don't even need to read the story. Well, I guess you could figure it out from the question itself, but the proportion that smokes in a randomly selected sample, right? The minute you say it's a sample, aren't you going to pick these two guys? Because it's a sample. And isn't it a sample that comes from this choice? Try to highlight that again. Nah. You agree? It's a sample proportion, right? Just means it comes from the sample, right? That's a population proportion. That would come from a whole population. Here's one to do with means similar. Okay, let's see this one. In a random sample of 300 parents in a school district, 111 supported a new education program. The purpose of this survey was to estimate what they believe the population of all parents in the school district who would support this new program. Now, what is the research question of interest? Well, it's this guy here. So we're looking for the proportion of parents in the school district who support. So we get that one. Now, what is the population? Oops. What is the population? And it's that one. What is the appropriate statistic or notation for this parameter? P. What's the value of the sample estimate? Won't it be 112 out of 300? And which one of these guys, 1 to 5, will you pick for that statistic? What symbol represents that 112 out of 300?
P.
Say again?
P.
Correct. Yeah. Are we good with these questions? Because I've just basically, here's 5 answers and they ask the same, similar questions at least each time. I'm just going through them, see that one's very like the one above, so I'm not doing that one. Oh, this one's a little bit different. Consider a situation in which a sample of 100 SAT scores was taken from the population of all people who took the test. Okay, seems reasonable. Which would be more spread out? Now, I do need to return because I haven't talked about this guy yet. We are going to talk about the sampling distribution. Now, give you a story to try and show you what happens here. Suppose I'm interested in P, which is a population parameter, and it's the proportion of adults who smoke cigarettes. Right. Now, if I had the money, wouldn't I just go and ask every single person? Hopefully I get the truth and I'd know the answer. Right, I could do a census, but I can't afford that. So what I do is I get a sample of 100 adults and I find out that 0.12 is my answer, right? 12% of adults say they smoke cigarettes. So far, so good. Now, would you agree that this number is a fixed number, right? It's it's 18%, it's 2%, but isn't this a number? Isn't this an estimate of that number? So what we did in statistics is we said, well, suppose I went and did another different 100 people, and I found out what percentage of them, what proportion of them smoke cigarettes. And the answer that I got was 10%. Can you imagine that could happen, right? A different 100 people, different number smoke. And then they did it a third time. And they got the answer. Can you imagine that every time you do it, you're going to get lots of different answers? Eventually, aren't you going to get duplicates, right? You know, 2 of my samples are both 14% or so on. Well, what you have to imagine is, imagine doing this thousands upon thousands of times. And then you take your data and you make a histogram of it. And we're going to show you what the histogram looks like. They always look like that guy. Do you recognize that guy? That shape? Anybody want to give me a name for the shape? There are a couple of names that come to mind.
Bell-shaped curve.
Bell-shaped, agreed. And there is another name that they have for it as well.
A normal curve.
Normal curve. And what they discovered is that right there at the peak, oh, by the way, you didn't know this until I told you right now, that the real answer was 11%. Somehow I actually got enough money off Bill Gates and I did it, right? Do you see that the samples that I got, none of them were 11%, but would you all agree they're within shouting distance? They're not like miles out, okay? Can you imagine, as I said, doing this lots and lots of times? Right there, right in the middle, is the real answer. These represent all the different samples. Now, can you see that sometimes I did really badly? And sometimes I did extortionately badly, but on the other side. But would you agree most of the time, I get an answer that's pretty close to 0.11. And this shape, this thing here, this whole process, it's given a special name. It's called the sampling distribution. So it's the distribution of all the samples you would get if you did them for thousands upon thousands of times. And it's been discovered that this is the shape you always get. They've done it through experiments, they've done it through the theory of the math behind it. And it ends up being one of these nice normal shaped, bell-shaped curves. We like bell-shaped curves because don't we have lots of ways we can use them? Remember, salt comes to mind, right? Later on, we'll use it like that for doing things. Now, when you have a normal distribution, as we have here, right, a sampling distribution, as I'm now going to call it, it has a mean and it has a standard deviation, right? And its mean is p, in this case, 0.11. And it has a standard deviation. Remember the 1, 2, 3, 1, 2, 3, that kind of thing? There is a formula that they have discovered for the standard deviation, right? How spread out this data is. And the formula, a little bit weird, but it works. It's p, 1 minus p, all over n. So it's going to be the square root of 0.11. 1 minus p is 1, take away that, so that's 0.89. And n is the sample size, so it would be 100. And so the standard deviation will be that guy. So I'll go square root of 0.11 times 0.89 divided by 100. And the answer is 0.031. Now, can you imagine me doing 1 standard deviation, 2 standard deviations, 3, and then going back 1, 2, 3, right? So couldn't I get a pretty good idea of what all the samples that would probably happen if they were size 100 in this world? Isn't there a chance that I might get a 0.14? Sure, but wouldn't that be quite unlikely? Couldn't I get a sample as big as 0.21? Yeah. But wouldn't that be like 1 in a million, right? It's not going to happen that often. So what this number does is it gives us, well, I like percentages. So 11% smoke, and this is what, 3.1%. What this does is it gives us a rough guide to how far away our estimate is likely to be. Would you agree that in this case, the answer is probably going to be around about 11, but it could be anywhere, 3 and a bit percent, right? 3% out. So I might get an answer as low as 8%. I might get an answer as big as 14%, right? But somewhere in that range is where most of my samples are going to end up. So imagine I have a different story and the P ends up being 0.71 and the standard deviation ends up being 0.25. So if I said to you, the answer is 71%, give or take 25%, in that world, wouldn't you be very careful about putting any particular confidence in my sample? Couldn't your sample be 25% out, right? It could be as much as, it could be 50 odds or 90 odds, right? Just as likely as it is to be 70 odds, right? So that would be something that I would not put a lot of confidence on. Is 3 and a bit percent, is that reasonable? Would you like better? I think I would like better. But would you say, that's okay? I wouldn't want to spend my house money on it, but I would be reasonably okay. Just for completeness sake then, suppose we did a different sample and it came out as that, and the standard deviation came out as 0.0005. So the real answer is 61%, but this tells me it's 0.05%. Would you agree that if my sample is likely to be out by 0.05%, wouldn't I be very comfortable with whatever my sample was? It's probably going to be really good. So right now we're just very, very basically talking about how good an estimate is my sample. And isn't the standard deviation that you get, this guy, a measure of how good my sample is likely to be. Essentially what we're saying. Are we good about that? Okay.
Sorry, my computer died.
Say again, please.
Sorry, my computer died.
Oh, so you just turn back up. Gotcha.
Yeah, thanks.
You're welcome. The next bunch of questions really don't go into anything, but we are going to return to these guys now. So we're on to our last section. This is where all the work is. Chapter 9, sampling distribution. Party. Okay. Now, where's my little notes? Here we go. So for any sample of size n, the sampling distribution will have a mean of p, right? And a standard deviation of that. We've already mentioned that a few minutes ago. P is the population proportion and n is the size of the sample, right? So you are going to get a bunch of questions where they tell you P and they tell you N, and it's your job to just calculate these two. So let's just focus on getting used to calculating the mean and standard deviation from a population. So for instance, in question 1A, they tell you the sample is 800 and the population proportion is 0.5, and you are being asked to find the mean and the standard deviation. The mean is P, and the standard deviation you get from this calculation. So it's really going to be plug and chug, isn't it? Now let's do the easy one. The mean is that guy. So I didn't even really need to do anything except write it down. The standard deviation is going to be P, which is 0.5, times 1 minus P. In this case, by coincidence, it's also 0.5. And then it's going to be divided by 800. And I'm going to go square root of 0.5 times 0.5 divided by 800. And the answer to 4 decimal places, because that's what they asked for, is 0.0177. And at this point, they don't ask you to describe why you're doing it or even what does this tell you. They're just asking you to calculate it. Are we good? Basically, that's what question 1 is about. And that's what question 2 is about. Now, if you think about it in real life, isn't it very unlikely I'll know the population parameter? Because if I knew that, why bother doing any of this? Don't I know the answer I was after anyway and I'd forget about it? What you tend to do is, don't you tend to have a sample? And when you have a sample, the mean is p hat, and the standard deviation is given a special name when it's a sample. And the standard deviation is called the standard error, SE for short. And the standard error of p hat. Now you look really carefully. Do you notice it's the exact same formula? So what's going to happen is you're going to get a story and they're going to say, we asked 200 people and 0.35 of them said, yes, I like Pepsi, right? Whatever the question is. Now, when you're given these two numbers, you're also going to be asked to calculate the mean, but now they're going to ask you to calculate that guy. And guess what? The mean is still p hat, so it's 0.35, and the standard error, although it has a different looking formula, would you agree it's really just the same formula? And so it's going to be the square root of 0.35 times 0.65, all divided by 200. So square root 0.35 times 0.65 divided by 200. And the answer to 4 decimal places is 0.0337. Are you okay with calculating the mean and the standard error when it's a sample question? Would you agree it's not that different from calculating the mean and standard deviation when it's a population question? And when you look at them, aren't they almost identical looking? Right. When it's a sample, you call it p hat. When it's a population, you call it p. The standard deviation is this guy. The standard error, although it's a different name, isn't it the same calculation? Are we good? Right. So let me show you some questions where we do that. In question 3, you are told that there were 600 people asked, and they asked, do you wear a seatbelt? And from that sample of 600, 180 out of them said it was 600. So do you see in this question, I had to actually calculate my p hat rather than them just tell me it. And then they go on and they say, tell me p hat. Already done. And in question B, tell me the standard error. P hat. 1 take away p hat over n. It's a plug and chug. 0.3, take away the guy, 0.7 over 600. And here we go. The square root of 0.3 times 0.7 divided by 600 is to 3 decimal places or 4, to 4 decimal places, 0.0187. And again, they're giving us no reason for why we're doing this yet. They're just getting you used to doing it, right? So we're kind of building up that skill set that you know how to get the p hat and the standard error. Are you good with this? You feel comfortable about p hats and standard error and p's and standard deviations? That's question 3. Does that? No. So I guess we're by the first 3 questions, just warm-ups. So now we are going to calculate what are called confidence intervals, even although they don't use that term yet. That's what they're going to use in later sections. We're going to find confidence intervals. And we are going to use a thing called the empirical rule. You might have forgotten that term, but hopefully you haven't forgotten this thing. Right in the middle is the mean. So let's just call it P for argument's sake. Can anybody remember what percentage of your data is going to be within 1 standard deviation of your mean? That's called the empirical rule. I much prefer the other name, but I don't want to give you the other name because it gives you the answer. I'll put the other name down in a minute. 1 standard deviation away from the mean. What percentage 68. Of the data? It's a 68. If you up it to 2 standard deviations away from the mean, what percentage of your data is within 2 standard deviations of the mean?
95.
Great. Okay, the ugliest one of the 3, because it's not a very pretty number. But if you go 3,
9.7.
Agreed. Which is why I prefer, instead of the name the empirical rule, I like the name the 68, 95, 99.7 rule. I know that's an ugly name, but isn't that a very useful name for what you do? It's just another name for the empirical rule. Now you say, well, how are we going to use this rule to kind of advance on what we've done? Well, imagine I have got, let's give you an example of that. Imagine that I have a sample of 200 people. And I wanted to know what percentage of them smoked. And let's say that in this country, it was 0.15. The problem I've got right now is a big one. How much confidence should I put in that answer? Because couldn't it be 15% and dead close? Or couldn't it be 15% and the answer could be anywhere, right? Right now, there's no obvious way in which I can do that. So what I'm going to do is I'm going to calculate the standard error, which is p hat 1 take away p hat all over n. So that's going to be the square root of 0.15 times 0.85 all divided by 200. And then I'll go over here and I'm going to find out what that is as a decimal. So square root 0.15 times 0.85 divided by 200. And let's just call that 0.025. So far, so good. Now, the empirical rule is going to kick in. If you take the mean and you add and subtract 2 standard deviations, don't you get 95% of the data? Right? And we're going to call that a 95% confidence interval. Now, I know what the mean is. It's 0.15, and it's going to be give or take 2 of these standard deviations, 0.025. Actually, to be really pernickety, the standard deviation is the standard error, right? So it's 0.15, give or take 0.05. So it's anywhere between 10 and 20. And since I like percentages, what we're saying here is based on this sample that we just collected, we are 95% sure that the real answer, right, is somewhere between 10 and 20%, right? We're 95% confident that the answer is probably somewhere in that range. Now, it could be as low as 10%, it could be as high as 20. In fact, any number between here and here is just as likely as the 15% that we got. Now, you look at that interval. Can you see that it's a pretty big interval, isn't it? There's a lot of places where the right answer could live. So my gut feeling is that that's not a very precise sample. Would you agree that the answer that you get is kind of grey? Yeah, it might be 10%, it might be 20. You know, there's quite a big difference, isn't there, between those two? One's twice the size of the other for starters. So I would not be too comfortable about putting too much weight on the 15%, right? It's a good ballpark figure, but there's lots of chances. Second feature is that if we're 95% confident that the true answer is in this range, doesn't the opposite of that mean that there's a 5% chance that we're just wrong? Completely way out, nowhere near the right answer. So isn't there a 5% chance that the answer could be any number? It could be 82%, right? Could be 1%. Are you willing to gamble on something where you're a 5% chance of being wrong? Well, it depends on what you're gambling on. See if it was, do you like Pepsi? I don't care if I'm a bit wrong. Would you agree? I don't care if it's 10 to 20% or there's a 5% chance. I don't even have a clue, right? If it was to do with medical research, wouldn't you probably want that to be a better answer, right? A tighter answer. I don't want to say this new medication somewhere between 10 and 20% effective, but there's a 5% chance it might kill you. I mean, I don't really want that. I'm exaggerating, but I don't want that to be my world. So we can look at that and use it. Question.
Yeah, can you do that for the 99.7% rule then with the third standard deviation?
Yeah, let's do that. 99.7%. Most of the numbers are here, except it's 3 standard errors, right? 1, 2, 3, right? 3 standard deviations, 3 standard errors. So it's going to be 0.15, give or take 3 of these. So 0.15 plus 0.075. So it might be as low as 0.075, and it might be as high as 0.225. So it could be 7.5%, and it could be 22.5%. So if you want to be 99.7% sure, do you see that your interval is even bigger than it was? Does that make sense that you would have to have a bigger interval to be more likely to collect the right answer, right? Does that make sense? Big interval, you're more likely that somewhere in that interval the real answer lives. Right? In fact, see if you wanted to be 100% sure, which is a pointless exercise in statistics, wouldn't the interval be 0 to 100%? Yeah, somewhere between 0 and 100% is the right answer. Well, that's useless, right? I can't go anything out of that. Right, let's do another one of these. Let's do a polling one. That's just a name when you do it with politicians, for instance. So let's suppose that I have a sample of 2,000 people. And in that 2,000 people, 51% of them say that they're going to vote for candidate A, right? 51% for candidate A. What do you want, a 95 or a 99.7? Which one do you want me to do?
95.
95. So we're going to use a 95% confidence interval. We are going to try and see whether or not this sample of 2,000, where 51% said they're going to vote for him, whether that proves that he's likely to win. Right? That's kind of the story. So the standard error is the square root of 0.51 times 0.49, all divided by 2,000. And if you do the square root of 0.51 times 0.49 and you divide it by 2,000, you get 0.011. Are you comfortable with that? 3 decimal places. Now, if you want to do a 95% confidence interval, won't it be the mean plus or minus 2 standard deviations? They're called standard errors here. So it's going to be p hat 0.51 plus or minus 2 of these guys. Which means it might be as small as 0.488, and it might be as big as 0.532. So it could be as low as 48.8%, but it might be as high as 53.2%. Now, if you were an unscrupulous TV channel and you liked candidate A, wouldn't your story be latest poll, candidate A is winning? 51% of the people are going to vote for him. He's going to win this election. So see you other people, don't bother voting, because this guy's going to win anyway, and it's a horrible weather, and you don't need to go out. Just don't bother. I'm being sarcastic here. That's called voter suppression. It is done. It drives me crazy when I see it. The purpose of this is a self-fulfilling prophecy. It doesn't matter if this is a true sample or not. Do you know the purpose of this is to make the people who want to vote for candidate B not to vote? Because if you think my guy isn't going to win, and only 2 or 3% of you are convinced enough that you just don't vote, doesn't candidate A win because of that? It's a self-fulfilling prophecy. It's called suppression of the vote. Totally legal. I've never heard of any TV company ever being charged with it, but be aware of that, right? It's one of the sneakiest ways they can stop you from voting, by making it seem like there's no point in you doing it, because the guy that you don't want is already going to do it. Now, you might say, but isn't that going to affect the people who would vote for A? Yes, it does. But what they've discovered is that it doesn't affect it quite as much. So maybe 1% of the people who were going to vote A said, well, he's going to win anyway. I'm not going out in that rain, so they don't vote. But there are 3% from the other side that don't do it. You see, the net worth is 2% and you win. Right? It still works. That's why they keep doing it, right? If it didn't work, they'd stop doing it. In reality, doesn't this say there is no clear winner? Couldn't you get 48.8% of the vote? Wouldn't that mean the other guy won? Couldn't you get 49% of the vote? Doesn't that mean the other guy won? Couldn't you get 49.9% of the vote and the other guy still won? Isn't there a lot of room there for the other guy to win? Now, what they should do, and in a good place they will, have you ever heard them say too close to call? Right, if they do that, then you are watching a reputable station, because they are telling you the truth. Would you agree that one of those answers is true, but every single one of them is just as likely to happen as any of the other ones? So you see, it could be a loss, it could be a win, right? They also use this term, within the margin of error. Have you ever heard that phrase? It's within the margin of error. And you might think, what's this margin of error they're talking about? See this guy here? The plus or minus guy? Not the 2 times them, but the final answer. That guy is called the margin of error. In this case, it's 2.2%. Now, if they're really good, right, if they're wanting to tell you all the information they need, they should say that candidate A got 51% of the vote, right, with a margin of error of plus or minus 2. They might, they might call it 2% just because people don't like 2.2s, right? You ever seen that? They do a thing and they say, right, it's 53% and the margin of error is 4%. You ever seen that kind of phrase? That's what they're getting at. So actually, you could do this if you had the money. Don't you just have to ask a nice random sample of 2,000 people and hopefully you ask it in a fair way and all the other things that could go wrong, and get this number. Because once you've got this number, this process is standard. Every single person will do it this way. They don't make up their own calculations, you know, and say, oh, well, I did it this way and got this answer. So what can they do? Well, couldn't you do a 99.7%? Now, if you did that, will you trust me that the margin of error gets even bigger? And so this interval widens even further. And so it's still too close to call, right? Now, can you imagine that at 99.7%, well, let's put some numbers in it. Let's suppose a different political sample, the 99.7% ended up being 49.8% and 51.2%. Let's just say it was that. That would be too close to call, wouldn't it? But if you did a 95% confidence interval, couldn't it become 50.2% to 50.8%? Now, if it was that one, wouldn't they say candidate A is now going to win? Because all of those numbers, aren't they bigger than 50%? Now, do you see that's a sneaky one, isn't it? It depends on what confidence interval you choose. You could come up with a different conclusion. Have you ever, because I've never heard it, have you ever heard any TV show say it was a 95% confidence interval that we used, or it was a 99.7, or any confidence interval? Have you ever heard them tell you what it is? Should you be suspicious about them not telling you? Well, if they're reputable, I don't think you should be too worried. But can you imagine less scrupulous? Remember suppression of the vote? You know, you only need to convince a few percentage of the people that it's not worth turning up. And if it's a close run race, that will be enough for your guy to win. So depends on your politics. So I bet each of you are thinking of a different TV channel or cable channel. And you'd say, yeah, that's the kind of thing that Fox would do. But my CNN would never do that. They're far too honest. Or you might think, oh God, yeah, I bet you that's what CNN does. And my Fox channel wouldn't dare do that. Since they never tell us, we'll never know. Agreed? You can't make them liars if you don't know what they do. So if they tell you margin of error, that's good news. At least they're being pseudo-honest, at least, or maybe purely honest. Any questions about that process? So we now have a way of not just using a sample to tell you what we think the real answer is. Don't we now have a way of putting an interval on it, telling us how confident we are that our answer is correct? Oh, and by the way, just to complete, if Fox or CNN says candidate A is going to win and they don't, do you know what they use as their excuse? 5% chance of being wrong, and that was one of the 5%. Which is true. If you do everything totally honestly, won't you be wrong 5% of the time? Right. So let's pick one. Who am I going to pick? This is question 6. Nice baby one to start with. They have a sample of 500 people. 350 of them said they believe in love at first sight, which is 0.7. And we are being asked to find p hat, which is 0.7, and the standard error of p hat. So just a nice baby one to get warmed up again. Well, I don't know why I keep getting 0.7s and 0.3s. I guess I'm just unlucky. And that's all they want. So square root is 0.7 times 0.3 divided by 500. And it's about 0.02. How many decimal places? 3. So 0.020. Okay, let's do one of the interval ones now. This is question 7. Suppose that the probability is 0.25. Oh, they're doing it from a population. That's cool. And n is 75. And we are going to find a 68% confidence interval. And then after that, that's going to be question C. And then question D, we're going to find a 95% confidence interval. I guess I should put A and B in. For question A, give the numerical value of the mean of the sampling distribution. Won't that just be 0.25? And part B, give the, oh God, here's a new name. I'm not doing it. I'll call it standard deviation. Would you agree it doesn't really matter if it's called P or P hat? If you've only got one number, it has to be that number, right? So that's the guy I'm going to use, and it's going to be 0.25, 0.75 over 75. So square root 0.25, 0.75 divided by 75. Oh, I guess they picked a nice number. That's what they were up to. Right, now 68% confidence interval is going to be the mean plus or minus how many standard deviations? 68%. How many plus or minus standard deviations?
1.
Just one. So it's going to be 0.25, give or take 0.05. How about 0.2 to 0.3? Or, as I like percentages, 20 to 30%. So evidently 20 to 30% of women believe in love in first sight. Okay. If you want to do a 95%, don't you just do 3 standard deviations? So that's what, 0.25.
Is it 2?
Rita, isn't it 2?
Oh, sorry, 2. You caught me right. It's 99.7, isn't it? That's 3. Thank you. So 0.05. So nothing 0.25, give or take that fella. So it could be as low as 0.15 and it could be as high as 0.35. So that would be 15%. Anyway, up to what, 35%. Now, do you see that that interval is small, but aren't you going to be wrong about a third of the time? Will you agree? Relatively speaking, that's small. It's smaller than this interval anyway, right? But would you really want to do a 68% confidence interval? In real life, I think that, and we don't use it, essentially, they just don't exist. Because I don't want to do something if 1 out of 3 times I'm wrong. Right? Would you want to trust your friend as telling you the truth if you know that your friend tells you lies 1 out of 3 times and you can't tell when she's lying? Would that be somebody you'd be comfortable with if they told you anything, right? I would, right? Okay, if you've got another friend who you know is pretty honest, right? And they tell you the truth 95% of the time, would you be more comfortable that any prediction she made is more likely to be true? In other words, 95% of the time, the real answer is in here. Are we good? Just for completeness sake, if you did a 99.7%, the answer would be somewhere between 10% and 40%. Would you agree that's a huge range? but at least you're 99.7% sure that it is somewhere in that range. Any questions about that group of questions? Looking at pictures, everybody cool? Right. Okay, next one I'm doing is question 8, or at least one like question 8. Okay, where are you? Abra, how long have I got? My watch doesn't, maybe it's telling the truth.
21 minutes.
203.
Okay, we're good. Right, you're getting the abbreviated version of question 8. Suppose medical researchers have discovered or believe that 0.7, 70%, is the proportion of teenagers with high blood pressure. Yikes. And they took a sample of 390 teenagers to test it out. What would the mean of the sampling distribution be? 0.7. What would be, what they're calling it? Oh, they're back to calling it standard deviation. So won't the standard deviation in this case be P, 1 minus P over N? Oh, this is getting annoying. Is there any combination that isn't 0.3, 0.7? I mean, is this not at least the third question that I ended up with a 0.7, 0.3? I'm just unlucky, I guess. 0.7, 0.3 divided by 390. And the answer to how many places do they want? 4. So 0.0232. And that is question A. And in question B, they want us to do a 99.7% confidence interval. So that's going to be a mean plus or minus 3 standard deviations, right? And that's going to be 0.7 plus or minus 3 of these guys. And that's going to be 0.7 plus or minus, no, not risk it, 3 times 0.0232. So plus or minus 0.0696. So it might be as small as 0.6304, or it might be as high as 0.7696. And then I looked at the question and I found out that they wanted this one to be rounded off to 3 decimal places. So you ever done that? You do a question in WebAssign 4 and then they tell you you're wrong because they wanted it in 3. Easy done, just be careful. I almost screwed up. But it's easy to convert, right? I know that's the answer, so I round it off. Okay. Do they want it as percentages? No, they want decimal places, so I'll call that good. I'm putting percentages in because I like them. 63, 70, is that a 6 at the end or what? 4, no? 70, okay. 63 to 77%. Now, what they then in question C is that they actually took a sample of 390, a real sample of 390, and they found out that of these teenagers, 215 of them had high blood pressure. And so 215 divided by 390 ends up being 0.55. How many decimal places do they want? I better do that again because they didn't give me accuracy. So 215 divided by 390. Yeah, okay. So 0.55 is what I'm calling it, which by the way is 55%. Is p-hat a parameter or a statistic?
Statistic.
Right. That was the little bit that went there. Then they go and they say, wait a minute. You collected this sample and you got 55% of them had high blood pressure. According to this interval, you should be 99.7% sure that the answers should come in that range. Why didn't this sample come in somewhere between here and here? Is this a guarantee that it's guaranteed to be in this interval? Isn't there a 0.3% chance that you're wrong? And guess what? We got one of the wrongs. But I think there's a good moral to that story. A lot of people think that statistics is telling you truths, like absolute truths. This is true. Aren't they not really doing that? Aren't we saying we're 99% sure, or we're 95% sure, or whatever the number we have, 98, whatever the number they come up with. But you're never 100% sure in statistics, because there's always a chance that you're wrong. Every single time. So you do everything right. Huge sample. You ask the question the right way. It's a nice random sample of people. You know, you go through the checklist of what you should do to make things work. And you still come a cropper, because isn't there a hole that you just got darn unlucky? Share a little story with you. Way back, I remember I was in high school. That shows you how good my memory is. And we were doing math questions, and I used to sit next to this really clever guy. And one of the questions that you would do, a typical question you might do in calculus, was that you'd have to pick a technique to solve a problem. And there are very often 2 or 3 possible techniques that might work, but only one of them ends up working. And it didn't matter whether I did technique 1, 2, 3, 3, 2, 1, or whatever. It was always the last one of the 3 that I ended up picking before it worked. I just was no good at, randomly picking a method and trying it out. And the friend next to me used to infuriate me, because after I got it, I'd say, oh, well, it took me 2 shots to get that one. He said, I got it in the first time. Every bloody time. Now, I can't put any statistics on that, but aren't I the kind of guy that would get the 0.3%? Because I just ain't lucky, right? And other people get it really well. So moral of that story is you're never 100% sure in statistics. All you can do is qualify it with a number, and then reasonable people will make a decision based on that. So, yeah, we got time. When can you use this method? Okay. The main one is number 1, but I'm putting in the other 2 for completeness. If you are going to collect a sample, right, and do this analysis, right, who are you going to vote for? Do you like Pepsi, right? Whatever the question is, there are a couple of things that you have to make sure that are true before you even do this analysis. Because if they're not true, I don't care what numbers you get, they're not worth the paper they're written on, right? They're just not worth it. First thing is, shouldn't you make sure that your sample is random, right? So if you're interested in people's opinion about taxes, would you agree it's probably not a good idea to go to your country club and just ask people there, right? If you're interested in people's opinion of abortion, it's probably not a good idea to go to a church and ask the people there. Not that people in church would lie to you, because I'm sure they wouldn't, but would you agree that you'd get a different sample with different people? So isn't a random sample a fair representation of everyone, right? Make sure that's true. We assume that in every question you're doing that that's true, so you don't need to worry about that. Unbiased question, haven't we, do you want to vote for that communist candidate A? Would you agree that's probably a bad way to phrase the question? Are you going to vote for candidate A, right? Or are you going to vote for that racist candidate B? Would you agree that's equally bad, right? So make sure the question's unbiased. So we'll take those two as granted. Now, the 10 rule is something you don't know. And the 10 rule says this has to be true. It basically says that you need a large sample, which you do. Would you agree it's not a good idea to ask two people anything and expect any decent data out of that, right? Who are you going to vote for? And you only ask two people. Won't the answer come back? Nobody's voting for them. 50% is voting for them, or 100% is voting for them. Now, you could do the number crunching and you could get an interval, but it would be pointless, right? So this is what this rule is. So basically it says the number in your sample times whatever the p-hat is must be bigger than 10. You might not know that until after you've done your survey, in which case you've spent a lot of money and found out you can't use the test. So imagine I got a sample of 200 people and 30% of them said candidate A. Then NP hat is 200 times 0.3, which is 60, and N1 minus P hat would be the other 140, and this one is good to go. Now imagine that you had another sample of 200, and P hat ended up being 0.04. So only 4% of them liked Pepsi, whatever the story was. NP hat is 200 times 0.04, and the number you've got here is 8. Do you see that's not bigger than 10? What that means is, don't do it. I know you've just spent a couple of $1,000 collecting this data. Do not do it. If you publish it, other people will do a peer review and you'll be a laughing stock and your reputation will be in the toilet. Everyone knows that you shouldn't do this analysis unless the 10 rule is true. Now you might say, but what about N1 minus P? That's 192, that's great, you're right. But for the rule to work, don't both of them need to be bigger than 10? Now you might say, why don't they just say, make your sample 100, right? Why don't they just have a rule, as long as you've got 100 people, you're fine. Well, that's one example of it, but here's an extreme version. Suppose you're interested in the percentage of Americans who have a very rare cancer. And so you spend a lot of money testing 100,000 volunteer patients to see if they've got this cancer. And the answer came back after all that hard work, right? That only 3 of them had it. If you do NP hat, can you trust me that it's not going to end well? It's actually just going to be 3. It's basically the number of people who say yes. Now, what about N1 minus P hat? I don't even want to calculate it. It's huge. If something is really, really rare, can you imagine only detecting 3 out of 100,000 is a very risky assumption? Could it be as high as 20 people or as low as 1 per 100,000? Right. So we created this rule to take account of the rarity of the event and the size of the sample together. And it's been discovered that as long as it's 10 or, technically, if you want to nitpick, a lot of books will allow 10. That's kind of grey area, right? You can use it. You can do all this good stuff. If it's less than that, don't even go there. It is just bad news. And we've got time. Have we got time for one more? I think I do. One last one. So I'm trying to pick one.
You got 6 minutes.
Oh, okay. Right. Well, I know I'm kicking out a couple of the questions at the end because I'm kicking them out for the other class as well. So this is the difference one, so I can't do them. What's the last one I can do that's good? Okay. This will be the last question. Once this class finishes, I'll go in and kill 11, 12, 13, and I'll put them on the part B one. So in question 10, an automobile club comes to the aid of stranded motorists who are members. Yeah, I'm a member of one of those. Over the long run, about 7% of their members utilize the service. So you're basically in the story told me that P is 7%, right? A small town has 700 members. They then say, let P hat be the proportion who require aid in a year period. Based on the empirical rule, what should be the interval? So they're just basically saying, I know they're phrasing it in a long-winded way, but find the 95% confidence interval. So it's going to be the standard deviation. So it's going to be the square root of P, 1 minus P over N. So it's going to be the square root. At least it's not 0.7 and 0.3, right? So at least I didn't have that. And let's see what we get. And the answer I'm looking for, what did I want? To the nearest hundredths, okay, 0.01 if you round that off. Okay. Then for a 95%, isn't it going to be the mean plus or minus 2 standard deviations? So it's going to be 0.07 plus or minus 2 lots of that. Okay, it comes out nice. 0.07 plus or minus 0.02. So 0.05 to 0.09. So somewhere in the region 5% to 9%. So in this town of 700 people, we could predict 95% confident that somewhere between 5 and 9% is likely to come out of that sample. Right, somewhere between 5 and 9% are going to use, are going to break down in the tow truck has to come. That's what this percentage is. Are we good on this? Okay, practical uses of this. Do you know that if you live in some places, your car insurance is a lot higher than other places, even if it was you and your twin brother, right? And you had the exact same car, right? If you live in some places, it's much more expensive to insure your car than others. Why does that happen? How did the insurance company decide?
Accident statistics?
Yes, and crime statistics as well. Can you imagine that you live in a place in Seattle where there is a lot of crime? And if we only talk about your car being stolen or damaged in some way, I mean, car accidents, of course, wouldn't you pay a higher premium in that area than if you stayed in the middle of Bainbridge Island where there's probably, I'm assuming, a lot less crime. Now, how do they calculate that? They put a percentage on what is the chance that a person in this area is going to claim insurance. Well, can you imagine one area might be 5 to 9% of the motorists in a year are going to put in a claim, and some other place it's only 1% to 3%. Can you imagine why the insurance premium in that area is going to be maybe half the premium on the other area? Isn't that the same reason why 19-year-olds pay more insurance than 22-year-olds? Don't they just calculate the percentage chance of an accident in each age group based on statistics and based on their p-hats, and you can make little intervals? I don't know what they use. Let's say they do 95% intervals. Can you see you can do a 95% interval for each situation, and the one that's got big numbers gets a big premium, and the situation that has the low numbers gets a smaller premium. And I think have I nailed it today, Abra? What kind of score do I get?
Oh, you're 1 minute ahead of time.
No, I'm not, because I want to spend a few seconds talking about your test. So I may be a couple of minutes overtime. So
Okay, I was
apologize.
actually going to ask you, are we still having our test on Monday?
We are still having our test. So let me spend it's going to be pretty easy. So while I'm doing that, if you haven't already, you say your last name for attendance purposes. I'm getting to when I find it. There we go. And here's our class. And we'll talk a little bit about your test. It's going to be on WebAssign. It's going to be the usual time. It's going to be on Monday. WebAssign will disappear except for that homework, just like last time. All the usual rules about turning up, video. Carbon copy test one, right? So I don't need to get into those details. So all I'm going to focus on now is what is going to be in your test. And here it goes. Chapter 6, gathering data. The one that a lot of people found trouble with, probabilities. Now, I can tell you right now, you're going to get, actually this guy here is, well, this guy here has 2 sections to it. The 9A that you're doing is in here, but I haven't upped that yet. So technically this is chapter 9 and 9A, but right, return to the study. Question on this guy, question on this guy, definitely questions on these guys. That one, normal distribution, intro and A. So 1, 2, 3, 4, 5, 6, 7, 8 questions, but at least 2 of those questions are going to be really short. Do you know the one we did at the start of today was, is this a parameter, is this a statistic? Those kind of ones. I mean, those will take seconds to do, so I wouldn't worry. They're not worth as many points for that. The hardest questions, I would guess, are almost guaranteed to be the probability tree questions, because a lot of people seem to have problems then. So you might want to focus on that because you're getting a probability tree question. Did anybody have problems with the regression line data? Is that easier, or was that just as hard? Well, I'm saying regression, I'm scanning in the wrong place. But you know how to gather data? That's to do with sampling methods, right? So do you know what a cluster sample is? It's full of words, and remember I spent a whole day just talking to you about cluster samples and simple random samples and convenience samples, and what are good samples and what were bad samples. So you can imagine those questions are going to be about picking from a list, 1, 2, 3, 4, 1, 2, 3, 4, 5. Anything else you need to know? I don't know if no questions is good or bad. Okay, watch this space because that's going to change because I had to break these guys up. So that's going to have a B and this is going to have an A. But apart from that, don't worry about it.
You're gonna send us the link again?
Yeah, you'll get a Zoom link. I don't know if I'm going to get it done today. I probably won't have my in-laws dropping in, but certainly by Sunday it'll be there. It'll be right at the top. Oh, my thing's going. Right at the top, it'll say test 2 information. So everything you need to know will be in there as well, right? Including the Zoom link for you to come to class. Turn up not half an hour, turn up 10 minutes early. Should be plenty of time to do it. I don't think too many people had trouble last time. Did you all finish plenty of time? Right, so it shouldn't be a time issue, I hope. That's it. If you're good, bye-bye.
Thank you.
You're welcome.
Thank you so much.
Not a problem. Bye-bye, guys. You're not allowed to have too good a weekend, but you might want to take Sunday and spend a bit of time with your kids.
That's the plan.
Right. If they really are bugging you, you could leave one of them with a stranger.
Okay, great, perfect.
Okay, just putting that out as an option.
Okay, thank you.
Okay, bye-bye.
Bye.